Go to science.
Okay, welcome to Code to Science, where we're going to be looking at the Earth and the solar system over the next few lessons. First, as always, there will be recap and remind questions. These should take no longer than 5 minutes.
Okay, now press pause to answer the questions. When you are ready, unpause it to check your answers. Okay, welcome back. The answers are on the board. Question 1, universal indicator goes blue or purple in alkalis. Remember doing the test with universal indicator paper, it goes blue or purple. Question 2, an acid has a pH value of 1 to 6. If you've put any number in that range, it is correct, but the range is 1 to 6. A neutral solution has a pH of 7. If we remember, the pH paper turns green, but green isn't the pH. The number is the pH, so the pH is 7. Question 4, a weak alkali has a pH of 8 to 10. Again, this is a range. If you've put any number between 8 and 10, it is correct, but remember that the range is 8 to 10. Question 5, we use chromatography to separate a mixture of coloured inks. If you remember the experiment that we did, we had filter paper on the desk, we put a spot of ink in the middle, we put water in. As the inks went out, the different colours separated at different rates. Right then, for this, you are going to need your fact sheet, which is also downloadable from class charts. The lesson that we are going to be doing is the Earth's structure initially, before we look at rock formation and then solar system. So what do we need to know? Well, firstly, our planet is a rocky planet in the solar system. And the picture that you can now see is the furthest image we have ever taken of our planet. And it was taken by Voyager 1 in 1990. This hazy structure is the solar system from Pluto, beyond Pluto, some 6 billion kilometers away from Earth. Voyager 1 took off in 1977, and 13 years later it got to the position where it could take this picture. The blue dot circled is our Earth. Now the blue dot is not oceans. It is just as part of light scattering off the atmosphere. It was smaller than a pixel when it was first taken. If we move further in, picture of our Earth starting to look like a blue-white marble that's taken from the moon in 1969. If we go further into orbit, we're starting to resolve land masses and oceans. We can see clouds. So we're now close enough to start focusing on our primary objective. What is the structure of the Earth, or what is the Earth made of? So our scientific question is, what is the structure of the Earth? The scientific skills we're going to be using today are observation, hypothesis, a making up an idea of what could be from our information, our evidence, and scientific modelling and diagram drawing. How you can measure your success. If at the end of these lessons you can name the Earth's layers, you can draw and label a diagram of the Earth, and you can explain how tectonic plates move. So what is our task? What I want you to do is look outside or look out of the window and write down and make a list of what makes the Earth. You must only use your observational skills for this, so you are saying what you see if you think that's what makes the Earth. You'll have 2 minutes to complete these observations, starting now. So that's 1 minute. Now, a good scientist always keep notes of what they do. So do make sure that you're jotting down what you see, your ideas, what you are thinking whilst you are carrying out this task. Seconds. 5, 4, 3, 2, 1. Okay, back with the lesson. The things you may have listed are the oceans, the seas, the rivers, and the water. You may have mentioned air, oxygen, the sky, or the atmosphere. You may have mentioned trees, plants, animals, and life. This is not what we're looking for. If these things were not here, the Earth as a planet could still be here. Things you should have listed are different types and sizes of rock, gravel, and sand, things like that. But the primary thing there is the different types and sizes of rock. So we can now start to build our initial model. Our first observations, or our initial observations, or more correctly our primary observations, we can say that the Earth is made from solid rock. And we can start to build our diagram, build our model based on this. So the structure of the Earth is rock. And I've labelled and arrowed to show what I have seen. All models, as we know, have limitations, and with each bit of information we get, we can make an improvement. Our primary observations suggest that the Earth is made from solid rock. The thing is, if this is so, how do we explain volcanoes. I would like you to modify your model to account for volcanoes using the reciprocal reader on the next page. Okay, go through the reciprocal reader, press pause now. When you are finished, press unpause and continue with the video. So based on our new observations, our information from volcanoes, we are able to make an improved model. And we've included the molten rock. Now at this stage, because we've got two layers, we give them a name. So the solid rock on the outside is called the crust, and the molten or liquid rock on the inside we call the mantle. Can you complete your improved model? However, again, there's a limitation to this model, and we're saying that the mantle layer is hot liquid rock. To make liquid rock, you would need a lot of heat, and where does that heat come from? Well, we can use the information that radioactive isotopes, when they decay, produce other elements and heat. So there must be radioactive isotopes to produce this heat to melt the rock. We can include that now into our model. So in the mantle, there are decaying radioactive isotopes to give heat.
There is still a limitation to our model. Let me explain. In front of you here, we have a directional compass. Now in the directional compass, there is a magnet and a casing. The north-seeking pole is the red end, the south-seeking pole is the south end. Now it does not matter which way you point your compass, the north-seeking pole will always face north. So you can see in this case, north is that way. This shows that the Earth has a magnetic field. Now, nowhere in our model have we taken into account a magnetic field.
So we've just seen from our directional compass that the needle on the compass always points north. And that is clear evidence that the Earth has a magnetic field. No matter where you are in the Earth, it always points north. Now the magnetic elements are iron, cobalt and nickel. But these are not in our model. If you want to find them, these elements are in the periodic table. They're in the middle. Use your school planner to have a look. Then modify your Earth model to include the fact the Earth has a magnetic field. So think about your iron, your cobalt, and your nickel. Pause now and unpause when you have found the elements and modified your model. This leaves us with our new model. What you should have done is now have a disk in the center. Now this disk in the center is the core. Now on mine, it's split into the outer core and the inner core, and this is where the iron nickel is. This now explains a magnetic field. And what we are left with is a model as shown in the fact sheet, the one that you need to learn, that looks like this. There we have the Earth. On the outside we have the crust. You can see it's a very, very tiny layer, no more than 70 kilometers thick at its thickest point. Then you've got the mantle, then you've got the liquid outer core, and then you have got the solid inner core. So where are we on our learning? Well, in front of you have this lesson's fact sheet showing the structure of the Earth. Now, we have looked at the label diagram of the Earth. We've looked at the thinnest, which is the crust at between 7 and 70 kilometers. We've looked at volcanoes. We've looked at where the core is, and we have looked at radioactive decay. This leaves tectonic plates, earthquakes, and why the plates move for us to do in the next section.